Hey guys, and welcome to the lab. If you work with self-hosted object stores, you already know what happened with MinIO and their soft exit from open source. If, like me, you were disappointed with their decision, you might be interested to know that we're starting development on a new object store called LabStore. The idea was born out of curiosity for learning how the S3 API works and the need to get back to writing code using a systems programming language. After giving it a little thought, we decided to pick Go. And we also brought in reinforcements for the web front end. Today we're gonna cover what happened with MinIO, how the community feels about it, and how this built the motivation to develop our own solution. In the lab, we like to learn, and we also like to produce open source code that stays open source. Stick around if you want to learn more about how an S3 object store works, the basics of Go, and how we started implementing one in Go. MinIO has grown to be loved by the community as the de facto open source solution for on-premise S3 object storage. Unfortunately, more recently they decided to follow a different direction, pushing all their OSS efforts into the background, which has resulted in widely spread negative feedback within the community. First, they removed critical features from their UI, which led users like me to keep running older Docker image versions, and others like the user on this Reddit post to create an alternative UI that brings back removed features. Unfortunately, the most likely outcome here is that those features will also be removed from the community edition backend in the near future, so this might not be a viable solution for the open source or self-hosting communities. Some users also decided to create a fork. It's called OpenMaxIO. And this is what's great about open source, it will remain open as long as someone maintains it. Unfortunately, there are also a few challenges here regarding trust and fragmentation. First of all, it's likely that multiple forks will appear, not counting the ones done for archival, personal use or testing. Some of them will also be quickly abandoned. Until we know that there are serious devs behind the fork and that users are adopting that fork, it will be hard to make a decision. The likely scenario here is that users will simply adopt another alternative for S3 object storage, completely dropping any MinIO related distribution. But it gets worse. Recently, MinIO decided that their community edition would be a source-only distribution, scraping their pre-built binaries, as you can see here, and also their Docker image. While it looks like they are keeping older images, they will not be building any new binaries or images for MinIO Community Edition. Regarding Docker images, users have been discussing the issue here and here, highlighting that while the community can build their own binaries or images, these might easily be compromised, which is a major breach in trust. But it gets even worse. On top of moving to a source-only distribution, they also ceased further development apart from bug fixes or security patches. The community has made notice that MinIO is no longer in active development. This is where they announced it. You can only install it with go install, and it will only be receiving bug fixes and CVE patches for now. CVE patches is security patches. It looks like they are turning their focus away from their original product and into their newer MinIO AI Store solution, developed on a separate codebase from what I understand and offering only a commercial license. I wonder if this strategy will work for them after losing so much karma with the community. Users are calling it a bait and switch, while progressively looking for other alternatives. Of course, it will be hard to get an alternative for the new features that AI Store will bring, as this competes directly with Amazon S3 tables, which supports the storage for Iceberg, Hudi and Delta Lake. So it supports data lake houses, no Duck Lake though. I wonder if this is something we can do in the future with LabStore. In all honesty, direction-wise, this is all great. It makes sense, I just don't understand the decision to essentially kill the open source solution. It could easily have been planned to fit their recent goals and with little effort avoid compromising the positive standing that they cultivated with the community. Regardless, if you're using MinIO, this is the time to make a decision. Either switch to AWS S3 directly, opt to pay for a commercial license for MinIO, or switch to another alternative. And there are a few like Garage, SeaweedFS, RustFS, which is quite interesting, and you can even use Ceph with their Ceph object gateway. In a future video, we'll test and benchmark these alternatives as well. But in short, this is what motivated us. You know, it's yet another solution. There are already some nice alternatives. You can keep using MinIO as it stands without new features and with everything that they removed gone, you know, user management, policy management, etc. But we decided we wanted to give it a go and try to build one ourselves. I mean, how hard can it be, right? And as you're going to find out, it's much harder than it looks. So now let's take a look at AWS S3 API documentation so that we understand just the dimension of this project. And so everything is properly documented. They have great documentation. We are looking at the S3 documentation here, but also we would need something like their IAM API so that we can manage users, groups, policies and all that. But most interesting is that each request for S3 is validated or signed by this AWS signature version 4. And this, while, I mean, it's a long implementation, right? It contains multiple elements, but more than that, it's very easy to, you know, fail and to add some new line or add an additional new line or encode the URL with some variation that doesn't fit the signature calculation, and it's very hard to debug. We have already implemented this, and there is also another version for chunked uploads where each chunk is signed and it uses the hash from the previous chunk. This was also recently implemented, so this is probably the hardest part to implement out of the whole API. But the next video will be all about how this signature can be computed. We'll cover it all and showcase our Go code to do it. By the way, it's already available and link down below in the description if you want to check it out by yourself. Now let's take a look into the S3 API. For instance, we've got our list buckets over here. This contains everything that we need to understand how to make a request, right? This is a get request to slash. Also, we are using path style URLs. This documentation is for virtual host style requests. So if we go into list objects, for instance, we'll find this request is done to directly to the root, but in our case we'll be adding the bucket name over here. This is what most open source alternatives for self-hosting do. We're going to implement, essentially we had to prioritize which actions to implement, and then for each action we also had to decide which headers are worth implementing. So right now we are trying to build a minimum viable product, and so let me just show it to you how we did this prioritization. So first we organize all the relevant requests and we categorize them by priority levels. We decided on 4 priority levels: P0 for critical, P1 for high, P2 2 for medium and P3 for low. For the MVP, we are focusing on the critical priority, everything that's absolutely required to make this work. For SIGV4, this might be optional if you are not that worried about turning this into an actual solution that people can use with authentication. But for us, it is very important that SIGV4 is implemented as a critical priority out of the box. So we already did this. This is done. It needs further testing, but it seems to be working. Then we collected a few critical requests. So everything that is CRUD for buckets and objects should be a part of this first implementation. We need to be able to list buckets, create a bucket, delete a bucket, list the objects in the bucket, and there are two versions here. We are still, trying to understand which one is higher priority, if one of them is higher priority. And then we've got head bucket, which just returns metadata. It is similar to list objects, but doesn't return the body of the message, just the metadata. Then we've got objects. We've got put object to upload an object, get object to download it, head object to get metadata about that object, delete, and copy object. Copy object will let you copy one object from a given bucket to another bucket, or within, I believe, the same bucket, but this still needs further research on our part. Then we've got the high priority, and we added multi-part uploads to this. This is not critical for the object store to work. The regular upload already has chunked uploads, so memory doesn't blow up, right? But if we want parallel uploads, then we need multi-part uploads, so this will be our next priority. We also added a few authentication based requests over here, so configuring the ACL and the policies for buckets, along with basic requests for IAM, like creating a user. I'm not sure about create login profile at this point, but create access key will probably be on this high priority as well. And the basics like listing users, creating groups and listing groups, managing groups. And other than that, for P2 and P3, we already have a basic top level list, but this will contain stuff like bucket versioning, encryption, object logging, CORS management for buckets, bucket configurations like covering the lifecycle, replication, logging, notification, metrics, and other object related actions like copying parts from existing objects during multi-part uploads, tagging, setting retention policies, etc. And as well as other IAM related actions like attaching global policies to users or groups. So at least we'll do everything on P1 and P2, and we'll see how the community interest grows about the object store, and our own personal interest develops, and we'll try to implement all of this stuff. And we'll begin by implementing the basics for each request, and add all the required headers as we move forward. So now everything that remains is for us to learn a bit of Go, and I've been learning Go for the first time during the last 2 weeks, and I already implemented SIGV4 with chunking support, with multi-chunk support as well. So it's been fun. It's been a bit hardcore to learn it in such a short amount of time, but very interesting. I ended up falling in love with this language. The tooling is amazing. The compiler is the fastest compiling I've ever seen. I mean, you can run Go code, compiled Go code, compile it on the fly and run it just as if it were a script. It compiles and runs as fast as you launch a Python script, sometimes even faster, because imports on Python scripts can take quite a while to run. if you know the LCTL from our Data Lab project, you'll see that once you run just the LCTL -- help, it will take quite a while to load because imports are not fully optimized, but you know, they are just globally imported, and they need to be imported locally per function to optimize that. I haven't done that yet, but with Go you can just, you know, almost use it as a scripting language. It's just much more verbose. Obviously it's a systems programming language, it's not meant for that, but if you are comfortable enough with Go and want to just do something small, you can almost use it as a scripting language because it compiles so fast. This is one of the biggest differences with Rust. The compiler is extremely slow. Of course, in Go you have a garbage collector, and this takes a few more CPU cycles. With Rust you don't have that, and that's why Rust tools are so amazingly efficient. But you know, writing the code and the whole process of development also needs to be you know, efficient itself. And so this is out of the top of my mind maybe the biggest reason why I decided to learn Go instead of delve deeper into Rust, at least at this point. But maybe in the future we can, you know, redesign a few components of LabStore using Rust, because they can integrate with each other without that much effort. And so let's go deeper into Go. And so a few first impressions I got when I started Go was I was looking at all these if statements with two statements instead of just one statement for the condition. What the heck is this? Or I was looking at the declaration of maps and finding that there is this almost dangling you know, type over here, because you know, there are no generics in Go, or rather originally it didn't support generics, now it does, and so the syntax just developed this way. Also there are two operators for assignment. What the heck is this? So let's go through this very short example. In for loops you've got, you know, your typical three blocks, three statements. Like for instance, you've got your initialization statement, then you've got your condition statement, and you can have a third statement that increments the variable usually, or you know, decrements it by 10 or whatever you need to do. And this is quite similar to that. So this is the initialization statement for your if, and then you've got the condition checking. And this is a pattern that we frequently use to check errors when no other value is returned. It just either fails or runs, and if it fails it returns an error. And so if this error is returned, it will be different than nil. There is no null here, it's nil, and then you can handle the error here. For maps, this is just the key type and return type for the map. And interestingly, when you declare functions, at first I didn't like this almost tangling int over here, but for functions, when you declare your function, you also do something like this or like this, you know. So it's not that different from declaring a function, so it makes sense that the return type for a function, or the value type, the return type for a map, is declared in a similar way. So the language is more consistent than it seems in the beginning. Also in here, notice that we are using two assignment operators, because this operator declares the variable and assigns it in one go. So this is essentially an untyped integer, because an integer, it could be, you know, an int, a 64-bit int, a 32-bit int, and notice that we have declared y, so we just assign it with equals. If we wanted to assign 10 to x and declare it, and then assign 20, we would use equals as well. So it's not that weird. Now let's look at the basics of Go. And like Rust, Go focuses heavily on composition, so this is the first thing that we try to familiarize ourselves with. So for instance, in here we are declaring a few types. We've got response, which takes a status code and a message. If you noticed, status code is lowercase while message is uppercase, so camel case versus Pascal case, and this means that this variable is not an exported variable, so you'll be able to access this variable within the package where this type is declared, but never outside of the package. This is like a private variable, but in Go they are called exported or unexported variables. Then we've got this error response over here, and if you notice this, we are extending response. So error response will contain a status code, a message, and also an error code, which is an integer. Then we define a different data structure to hold a user session with a user ID and a token. And we define this login success response, which extends response and provides a field called data, which is of type user session. Okay, so this is the basics of composition with types. Already covered this. Public, private doesn't really exist. It's just exported or unexported. Exported is uppercase variables or Pascal case. Unexported is lowercase or camel case variables. Then we've got something interesting as well with serialization, which is we don't really use the term serialization in Go. We call it encoding generically and marshalling and marshalling. For serialization, there are these annotations on structure types over here for each field. These are called tags, and these tags can be used to set some, and are usually used to set some serialization options. For instance, for this user session type, when we export it as JSON, this will be called user ID will be exported as ID, and we are not going to serialize the token with it because this is private information for security reasons. So for instance, if we define a user session, and as you can see we are using brackets over here, and we are defining a user ID, which is a UID, and a token, and then we are applying JSON Marshal to this, and we are ignoring the error, which you should never do, but just for this example we will. And then we are converting this data into string, and something like this should be returned, so only the ID with the user ID, no token, right? Another thing we can do in Go is declare enum-like constants. So we don't really have enums in Go, we don't really need it either, and so we've got this iota, and iota is kind of like an utility function or a utility keyword that you can use to automatically increment constants. So for instance, we are ignoring the first value of iota because we want to start at 1. We could also do something like this, iota plus 1. And we are just declaring each of our enum elements over here. They are constants, individual constants. So we'll have starting, which is of type status, which is an int. This is something that is recommended that you do when you declare this type of enum-like constants. You just create an additional type for it, which is always int, but give it a name, right? And then our starting is of type status. It will be iota plus 1. Running, failed, and success will also be of type status because this gets inherited. And so we'll have iota plus 1, plus 2, plus 3, plus 4, right? And so we have our, our constant. our enum like constant. And we could also do, because we declare this type status, we could do something like a function of type status, and keep in mind that this status can be one of the constants that we defined, or an invalid status that is outside of this range, so we need to handle it. This is not like a common enum in Python or some other language. You need to handle it. In Rust, I believe you have, native enums. In here you don't. That's fine. And so once we run status description, it will print process is starting. If we do it with an invalid status integer, we'll get this instead. And this brings us to receiver methods. As you can see, this status description could just have been something like, instead starting dot description, or status 1000, which is invalid but might be user input dot description, right? We usually have this status declared in a variable. Let's say it is starting, and then we are printing this, right? Okay, so we can redefine it using receiver methods, and you just use this initial syntax instead of using the parameter, and it's just much cleaner. Just call s.description, so it's status.description. It's a cleaner way to define this. Then let's go into error handling, and this is very specific to Go, the way this is done. It is somewhat similar to how you do it in basic C, but there are a few utilities as well. So you can, first of all, you can just call panic. Some people do that. They call panic, the code just stops there, the application exits. You can also, some libraries have this log fatal, for instance log Rust as this, and log fatal will print a message using the logger and then also exit like panic does. And you can even intercept panic, but usually don't do that, you avoid that, and instead you use proper error handling. Let's take a look at how error handling works. So perhaps the easiest way to handle errors, and this is something I'm not covering here, but I'll give you an example. So for instance, let's say we have a function that does some work, and it might fail, right? It returns nothing, but it might fail. You just return error, so our return type will be error. We'll do the work, right? And if there is an error, we can just return something like error.new, which is the first function that I'm showing you here, or rather errors.new, and then my error message. This should be always lowercase because this can be composed. There is this format error f, which can take a %w for wrap, where you wrap your error into another error. So this will return a new error that says server error with the string message for the previous error. And you can actually unwrap this and use and have access directly to the internal error as well. And so this is one way to handle it. If there are no errors, just return nil, right? And this is how basic error handling works. Sometimes you need to return a value. Let's say we want to return a string. If you return a string, then if there is an error, this will be nil, or rather for strings it will be an empty string. But let's say that we are returning an object. Let's use one of the previous ones that we declared here. So for instance, response. Let's say that we are returning a pointer to response. So if this failed, there is no response, we return nil and an error. If it didn't fail, we'll return our response. Let's say it's on variable resp, and we return nil for the error. Never return nil or return resp and an error, right? Avoid this at all costs. This is much cleaner to do it this way. This is like basic error handling. Of course, there are a few other features that I enjoy a lot, like defining your own error structure. And you can define whatever you need to handle your errors. For instance, we are trying to define a standard error structure for S3, which will be used to serialize the XML response when there is an error. And if you decide to do this, we just need to implement the error method, which will return a string with the error message for this your specific data structure. So you can just declare your error like so and return it as an error, right? And everything will work without an issue. But you can also use these methods, error is or error as. And these methods, error is just checks whether your error is of a given type, like S3 error, and error as also tries to convert this, cast this into a given type. So for instance, if we have a generic method to handle errors, and this is very similar to what we are currently using on LabStore, let's say that we get an HTTP error, we have this method to handle it, we log it to the console, and we don't need to know the type of the error to log it, right? Because it implements error, it implements this method, right, which returns a string with the error. But we might want to, you know, write an XML response for this particular error, so we can just run errors.as error and try to cast this to S3 or load it into this structure. If this is not compatible, then this will return false and the else or the other conditions will run. If it returns true, then we can, you know, use the data structure and write the XML. So this is a really nice way to handle errors. I prefer this to exceptions, to be honest. I think this is much cleaner, and it motivates programmers to actually have to try and you know, handle the errors as they write their code. And finally, this is a fringe case, but let's say that you have you are developing your web server, and one of the libraries that you are using decided that calling panic was a nice thing, and you want to intercept panic. So if you do this, let's say that we have this panic demo is called, and we have other instructions. Let's say the next request on your API would be processed here, and this is one of those requests. If we have this deferred method, and deferred methods are another one of the features of Go, you'll frequently see something like defer f.close or something like this, and this means that this method will be run once the function returns. Doesn't matter where it returns, it will run during return. So in here we've got this deferred method to handle a panic, and this method uses the recover function, which intercepts the panic. Recover can only be called within deferred methods, so this is the only way you can use it. And then we have our panic request, which calls panic and would exit the application completely. So once we call a function that runs panic, because we have this defer, it will recover from that panic, but it will never print this message. However, it will continue running outside of this function completely normally, right? So if you get into the fringe case where you need to intercept a panic from another library, this is how you do it. Then there are a few conventions that I found. particularly for the suffixes of print related or log related functions. So if you don't have any suffix, for instance format print, format sprint, or for logrus you've got info or debug or any other level, this will concatenate all the arguments. It will still print a new line, but they are concatenated without spaces, right? So for instance, let's say that we called format print, and we've got my thing, and we've got your thing over here. This would print something like my thing, your thing, right? However, if for ln methods, and keep in mind there is still a new line here, right? For ln methods, if you do this, then there will be a space over here. And most of these methods essentially use %v for value, which is a way that you can format your, so for instance, if you used printf, you might use %v over here, and then let's say that we have an error structure, an S3 error over here. This would just print something that is useful for, you know, to debug this data structure. So this is like if you print in Python a variable, this is how you can do it the same way in Go, without the need to, you know, parse anything or serialize anything. And then I already showed how f works, and then these are some fringe cases. It only happens on logrus, but you've got this fn suffix as well. It just takes a function for when you have a complex logging workflow and you need to process the message somehow. You can just give it a function, but this is not a convention. This is just for the sake of completion, since we are talking about logrus. These are the convention: no suffix, ln or f for format, right? And finally, let's talk net HTTP. There are many discussions about what the best web framework for Go is, and I ended up going with you know, the standard library net HTTP. At first I thought it was a good idea to go with Fiber, and let's take a quick look. So I at first, because I needed a router, and I thought I had to use, so if you go into package.go.dev, I thought I had to use an external library for this. There is HTTP router as a very basic router that you can use. Because I thought I had to use the library like this for routing, I went searching for some benchmarks, and this is from 2022, I believe. They compare a lot of these web frameworks. And as you can see, there is one that distinguishes itself quite a lot, which is Fiber, which can handle a lot more requests per second. And if you go and take a look at the allocation in megabytes, you'll find that it also allocates so little memory to handle all of this. So I decided to refactor everything using Fiber. But I ended up learning that these benchmarks were slightly outdated, and there is a more recent benchmark for 2024 which shows something a bit different. So this Gene and Echo are built on top of net HTTP, so they are slightly slower than net HTTP. And if we go and look at the charts, for instance, for requests per seconds, the difference is not as dramatic as the other benchmark, right? Of course, Fiber still wins in requests per second, and it still wins if we go and take a look at memory usage. It still is in memory usage. It's just not such a wide gap. And so after a while I understood that actually the native library, the standard library, provides this HTTP servmux, which is its own router, so you can do stuff like this natively. And I ended up, migrating back because I didn't want to get locked out of the whole ecosystem. There are many utilities that you can use with NetHTTP, but the nail on the coffin for Fiber is that it's built on top of fast HTTP, and fast HTTP is not completely RFC compliant. And because I'm building an object store here that relies quite a lot on the standard for HTTP, because we need to compute stuff like SIGV4, which is very, the slightest change will produce an invalid signature. And so I didn't want to risk that, and I migrated back, and now we are using the native multiplexer, this router over here that comes with NetHTTP, and it's working fine. I only had this issue where these two routes were not being properly distinguished, so it would always match. Even only 4 bucket will always match this route, because requests were getting here with a backslash, and so I just added this middleware that removes the slash, and it matches this perfectly. We might need to update this in the future because it's only trimming this and ignoring params, get params, query params. But for now it works, and it will be added as we need it during development. And so if you ever get into the thought process or the decision process to pick a web framework to work with on Go, just go NetHTTP. You can't go wrong with NetHTTP. If performance updates are added to the language, you'll benefit from all that. You also benefit from the ecosystem, and you get all the basic tools for routing that you need to implement. You can do middleware. We are doing middleware without any issues. As you can see here, we've got this IM middleware that we are already including, and so this is working perfectly fine. But so now that you know some of the basics of Go, let's look at the code, how we organized our repo and all that. And here we are on the first version of LabStore. It's got little support yet. You can create a bucket, delete a bucket, put or copy an object into a bucket. But you can't, for instance, list a bucket yet. The main feature and that we implement is signature v4. That was probably the hardest part we had to deal with. From now on, it will be just implementing each request, and it will be a lot of work, but not as complex, so it can flow quite more easily. So in here we've got a monorepo structure. Our two main projects over here are the backend, which we are talking about today, and we've got the web front end as well, which is being developed in Svelte by a friend of mine. And so we've got other stuff like infra. We've got this compose that just runs MinIO so that the front end can test everything without having to integrate immediately with the backend. We've got this share to keep, logos and other stuff. This is for documentation, and we have an overview on the API for S3 over here. You can check it out if you like. The CLI project will contain a command line utility that will let us manage both the front end and back end. Everything will be integrated here. This will be our entry point to LabStore, so it will be something like a command called LabStore. And then we've got our backend, which is what we're going to talk about now. So we've got a command here, which will be called LabStore server. If we want to run it standalone, we can do it. So we are using, we have this root command over here. We are using Cobra for our command line handling. In internal is where we've got most of our code, and there is package, which is code that will be exposed, so we might want to reuse our logger, and we'll want to reuse our IAM from over here, because we'll call it from the CLI application for sure, to help us manage users, or maybe from the front end, but front end we'll probably call the REST API, right? And in here we've got our authentication, so we've got our signature validation code. So this is kind of a real use case. Of course, we've got a lot to do still, but for now, this is how you handle with net HTTP. You can verify requests. You can access headers with our header gets. We get this authorization, and then we get all the headers that we need to do the computation. For instance, in here you can see an example of the strings library, where we do cut prefix from auth, and we are just removing this part of the string, which indicates this is a SIGV4 header, and this returns on success. It will return the string without the prefix, and if it fails, in this case they return just a boolean, not an error, and you check this boolean, and then we error handle like I just taught you in the previous clips. And so in here we didn't cover the for loop. A lot of the times we use this range keyword, and these parts are, this is an array. Range will iterate over this array, and it will give you the index, which we don't need here, and each value. So this is kind of like a for each without the index, and so forth. We are using log Rus for logging. As you can see, this is not properly idiomatic, so the right way I should have done this, because I was learning, would be just to do it this way, right? Because this way it will print space using ln, and we can change this as we are refactoring later. And yeah, this can get quite complex. We'll go into all of this in the next video. We've got one for chunked streaming as well. So the way we are segmenting our code is, for instance, 4 buckets. We've got all of our operations here. We are splitting business logic from HTTP handling. For instance, for list requests, this would be our business logic, and we are keeping everything within one file for now. It's quite short, so there is no reason to move this out of here. But we still keep it separate, because, for instance, when we migrated from Fiber back to net HTTP, we had already done this split into business logic and HTTP request handling. It's the same for create bucket. So it was very easy to switch into net HTTP like this. So, for instance, if you need, let's take a look at our router first, perhaps, and the router is defined in here. And for instance, we were looking at create bucket. So create bucket is this request, this first request over here, and we are calling this handler function from here. And as you see, there is a path parameter, which is bucket. And if we go into this method, which we were just looking at, you'll see that I'm using from the request the path value bucket, and this will return that path value. For multiple path values, you can use these 3 dots and they will return everything from bucket onward. So for instance, for put object handler, we'll still get the bucket as path value, and we'll get the key exactly the same way. This will contain all the path from bucket onward, right? And so this as you can see, this is working code, and this is quite easy to implement. Of course, it's not completely implemented, not the headers are not completely handled, the response is not complete, but this works, right? This already works. For configuration, we've got this generic constants over here, and we've got this environment variable based configuration that loads a .env file by default or just uses the configuration you provided. Then we've got this error handling. We were just looking at this data structure, and one pattern that is very common in Go is to do something like this with request ID. So for instance, let's say that we define this S3 error, and then we want to add the request ID to the error. We can just pick up the key, and then with request ID something, and give it the error ID over here, and then with host ID, and you can give it the host ID over here. So this is method chaining. You can do this very easily on Go. Then our middleware looks something like this. So we just implement this function, and in my blog post there is a link to a video by Dreams of Code who explains this wonderfully. So go check out this video if you want to learn how to implement this properly. That video is really a must watch if you want to use net HTTP properly. And so this is how we implemented. In here there is the logic to decide whether we are using chunked headers, and we are verifying that signature for each chunk. We also handle compression. It's not fully implemented, but we have some basics over here. Then we've got our methods for objects, and we've got our generic service methods over here. This will probably move outside of service and into buckets perhaps, but this is how our project is organized so far. You can also take a look at our GitHub repo if you'd like. We created a GitHub org for this called IllumiKnow Labs, because this is not just me working on this now. This is now a larger open source project, and it's me and one colleague working on the front end, but we did this separately. So if you like, you can go check out the repo already. In here we are doing release branches for the backend and the front end. So if you want the latest version for the backend, you would go here, for instance. Most smaller issues are integrated into this branch or merged quite quickly. And we are managing our project using GitHub projects, so completely within GitHub. The board is a Kanban board. It's not visible to the community, but if you open an issue over here, we would get it on an uncategorized column, and we can add it to our workflow as we decide. We are also tracking all the issues for the backend in here, so these will be the next two that I will be picking up, and that's how it is. Right now we are having fun, learning a lot, and we'll be sharing what we learn with you, the community, as well. So before leaving, I will just quickly show you how this works. I'll show you a quick demo of this running. So the backend is now running, which means that we have an object store running. LabStore is running, right? And now we can just run something like, I've got a LabStore alias here, okay? So I can just ls LabStore, for instance, and you'll find that it is working, right? We use this a lot to help us debug the requests. Let's say that we want to create a bucket called test, okay? And let's ls again, and there is test. And let's say that we want, I'm going to create just a random data file. And let's say that we want to copy our TMP random data to LabStore test. And as you can see, it was copied, but unfortunately we can't yet list. So if I try to run a list on test, we'll get nothing because this is not implemented yet. But as you can see, this is already working quite well. We are using for testing, let me just show it to you. We've got this just file with a few commands that I use for benchmarking and testing. And for benchmarking, we are using Warp, which is by MinIO. RustFS also uses this for benchmarking. We are not getting high performance values yet, far from that. It will take quite a while to just be on the same level as other tools out there, of course, because just started. And we also implement a few tests with MC by MinIO, rclone, or even S5CMD, and all these work differently. They do different stuff. So let's just try to test. So there is this just backend, and we can benchmark. Let's see if it works, crossing fingers, right? And as you can see, the benchmark is now running. And yeah, this is quite inefficient still. If you compare this to RustFS, it's not even a valid comparison because we are running on the local host, and I think they used 15 gigabit network to test it, so these hours would be even slower compared to that. But yeah, we still need to implement the MVP, then we will need to optimize it, and then we can extend support to other more secondary requests. But I mean, I'm quite happy with this initial result, and I hope you get excited about LabStore as well, and IllumiKnow Labs in general, because we are trying to build something where we can all learn together and produce cool open source code together as well. Always stuff around the web and stuff around data as well. And that's it for now on LabStore. Next week we'll do a quick video with a few additional details on how SigV4 works, doing a step-by-step code tracing to understand each element required to compute the signature. I hope you enjoyed this week's video, and if you did, be sure to hit that subscribe button so you don't miss future videos on LabStore, our Go adventures, and other fun videos always around data, infrastructure for data, and also soon some philosophical reflections on the new world of AI, privacy, freedom, and overall constructive thinking for a builder society where we create rather than destroy, growing together to become better. I'll see you next time. Over and out.